Hello, everyone, and thank you for attending this presentation, which is entitled Enabling Wireless Integration of IoT Applications for Context-Aware Environments. In the first place, I would like to thank the organizers of the International Conference on Multimedia and Computing and Systems for proposing me this presentation. Thank you very much. So my name is Francisco Falcone, and I am Associate Professor at the Public University of Navarra in Spain. And today I will be sharing with you some of the research topics in relation with wireless system integration and IoT applications. Now, in the first place, it's interesting to put into context what we describe as these context-aware applications, and it is compulsory to think about the concept of smart cities and smart regions. Now, it's a studied fact that by 2050, the vast majority of the population, around 70%, is going to be living in dense urban areas. This poses challenges in terms of providing sustainability as well as in providing adequate quality of life to the citizens of these large urban areas. In this sense, the concept of a smart city arises as basically the conjunction or integration of multiple complex systems in order to optimize the overall operation within these frameworks. So in the case of a city, for example, we have multiple systems that are going to be working. For example, one very known case is the case of the energy system. So we can have the electrical grid. And here comes into play the concept of the smart grid, where we can control in a more precise way the way in which electrical balance is performed, or the way in which we can handle multiple types of renewable energy sources. Another important system in relation with the operation of the city are transportation systems. And in this case, the paradigm within smart cities would be intelligent transportation systems. They would be dealing with elements such as connected vehicles as well as autonomous vehicles. And here it's interesting to note that we can optimize the operation within a city by, for example, providing precise route planning in order to decrease travel time as well as acoustic pollution and particle type pollution, as well as providing a more sustainable and greener environment. Um, we can also have waste management in order to control issues such as the way in which recycling is performed. And we can also manage elements such as hydric resources and the control of water usage within a city. So basically, in order to do this, we are going to have to depend on multiple elements in order to have this integration performed. And there's going to be multiple issues, such as the way in which these systems can interoperate, the way in which we can handle big amounts of data, how we can have seamless and easy integration, and also the way in which we make these systems centered in the user and not in the systems themselves. Well, in any case, in order to provide this context awareness, communication systems are going to play a key role. And in this sense, in order to provide high levels of ubiquity and mobility, wireless communication systems are going to play a key role in order to enable interconnectivity and data exchange from sensors and actuators. So there's a myriad of wireless systems that we can use, which are going to be employed as a function of the coverage capacity requirements that we are going to have within the area of operation of these systems, as well as considering the specific application in which they are intended for. So giving a brief summary, we could have mobile systems, which would be these public land mobile network elements. And here, basically, we're going to span from 2G, 3G, 4G, and more recently 5G communication systems. Now, these are going to be very, let's say, flexible systems, and they're going to be very adaptable for a very wide array of applications. In the specific case of Internet of Things, we're going to have very specific solutions in order to provide high levels of connectivity in wide areas, and considering the fact that we are going to have intrinsic limitations in terms of energy consumption and form factor and cost. So in the case of previous systems, we would have machine-to-machine type communications, and these would be handled by GPRS connections. Now, in the case of, for example, 4G, we're going to have specific solutions in order to provide Internet of Things connectivity, such as narrowband IoT or LTE Cat M1 and Cat M2. In the case of 5G, we are going to have specific device-to-device connectivity solutions that are going to be devised in the near future. Now, depending on the application, we have other types of wireless systems, basically wireless sensor networks and wireless local area networks. And these have become very popular in recent years, given the fact that they have been designed intentionally to support a vast amount of devices within a wide range of area coverage, and in principle, considering the fact that it's going to have intrinsic energy restrictions. So basically, in this case, what we are going to have is multiple standards, mainly based on 802.15.4 systems, as well as proprietary systems. And here we have systems such as Zigbee, which are very popular, or long-range LoRaWAN systems, which are low power, wide area communication systems. And we have other solutions which are more on the proprietary side, which are also very interesting, like an Ocean, which is going to be based on the use of energy harvesting mechanisms in order to provide the required energy to operate these devices, or the proprietary Sigfox standard, which is very interesting in terms of having infrastructure that is leased to the solution provider. Now, in other applications, we require more local area connectivity, and in this case, we are going to be making use of wireless body area networks and personal area networks. Here, we're going to be considering systems such as Bluetooth and Bluetooth Low Energy in order to form pico-nets of communication. We're also going to have systems such as near-field communications, which have become popular for identification as well as for wireless mobile payment systems. We also have very popular RFID systems, which are used mainly for tracking and, let's say, logistic purposes. And more recently, we have new standards based on intra-body magnetic coupling-based communication, which are interesting in terms of providing high levels of security. So as you can see, we really have a vast range of systems that we can use, and they can provide very interesting solutions. And wireless links are going to be very interesting in terms of being very flexible and adaptable. And as we know, we're going to be employing radio waves as the physical media in order to propagate our information from end to end. And we're going to have some very fundamental characteristics in relation with these waves. They're going to have an amplitude and some frequency in which they're going to be operating. And of course, they're going to have some sort of modulation encoding scheme as well as some specific access method. So these are going to be mainly derived in order to provide a specific bit rate and therefore complying with the requirements of the application. Now, the specific item that we need to consider is the fact that in relation with other cable systems, in the case of wireless systems, the electromagnetic waves are going to interact with the surrounding environment. And we have to consider that we're going to have losses given the distance effect. We also have to consider the specific medium in which we're going to propagate, because we're going to have atmospheric absorption losses, and we're going to have the effect of hydrometeors, such as, for example, hail or snow or rain. Moreover, electromagnetic waves in general are going to follow Fresnel laws, and we're going to have reflection, refraction, diffraction, and diffuse scattering on rough surfaces. And moreover, depending on the specific application, like for example, in the specific case of vehicular environments, we have added issues to the previous ones, like the fact that we have a strongly metallic environment, the location of the antennas within the vehicle embodiment, which is going to be complex because they're going to heavily degrade the behavior in terms of the radiation diagram. So all of this has to be considered. So bottom line, it's an easy to deploy channel and it's very flexible, but it's a very variable and hostile channel. Moreover, it is initially it's a very easily detectable channel. So maybe we also have some additional constraints and issues in terms of security. So it's compulsory to understand these effects in order to try to perform radio planning tasks and eventually system level analysis in order to see if we comply or not with the requirements of the overall systems. Now, one of the first things we need to consider is the fact that if we are talking about propagation in Earth, basically we're talking about tropospheric propagation, and this is going to be affected by the dispersive nature of the diatomic molecular gases which we're going to have within the atmosphere. So electromagnetic waves are going to be propagating within the atmosphere, and they're going to be interacting with these diatomic molecules that are going to be present in the gases, basically exchanging electromagnetic wave energy and converting it via the imaginary part of the dielectric constant into heat. So depending on the contents, which are going to be given by the specific region in the world and the height at which we are in, and of course the frequency range in which we're operating, we're going to have lower or higher losses. Of course, as frequency increases, these losses are going to be higher, and therefore we need to consider the impact of choosing the specific frequency range. Let's say that in RF and microwaves, the specific effects are not that big, but as soon as we start going into millimeter wave range, as you can see, we have losses that are pretty considerable in terms of the effective distance. So this is something we need to take into account, especially if we're considering future 5G bands, for example, in the initial 26 to 28 gigahertz, or we consider the 802.11ad bands of Wi-Fi, which are within the 60 to 70 gigahertz range. Now, as we said before, we need to consider the impact of the wireless channel, and this is given by the fact that we need to obtain quality of service and quality of experience metrics in order to analyze and see if we are complying with the requirements of the service. Now, this can be done in a very simple way by providing a link balance analysis in which basically we need to determine the received power level, and we need to consider if it's going to comply with the sensitivity level of our receivers. And remember, sensitivity levels of receiver is not a static value. It's going to be dynamic, and it's going to be depending on elements such as the modulation scheme, the coding that we're employing, the binary rate, and hardware effects such as the noise factors of the elements that we are putting in our transceiver chain. So basically, these elements are going to be variable, but especially the radio propagation losses are going to be highly variable because they're going to be strongly depending on user dynamics as well as on the variations within the wireless propagation channel. So in order to understand what is going to go on and see if really we're going to comply with this received power level comparison versus the sensitivity, hence coverage capacity relations, we need to analyze them and compute them. Now, in order to do this, what we need to do is to perform radio propagation estimation. And this has to be performed in a way in which we comply with an adequate balance between the accuracy that needs to be obtained within this estimation and, of course, the computational cost of the method employed. Now, on the high performance side, we're going to have full wave electromagnetic simulation, which can be employed in order to estimate wireless propagation. And in this case, we are going to be dealing with elements in which we are going to obtain the value of Maxwell's equations within the full volume of space. And this is going to be done in a numerical fashion. And in this way, we are going to have solvers which are going to solve Maxwell's equations based on finite difference time domain, for example, or finite integration time domain. We can also employ methods such as method of moments and finite elements. Now, these solutions are going to be very precise, but they're going to be computationally very costly. On the low accuracy side, we're going to have empirical statistical methods, which are going to be usually based on statistical linear or nonlinear regression from a cloud of points of measurement obtained in a specific area. Now, these solutions are going to be very simple. In the end, we're going to obtain a parameter-based equation, which is going to be very easily solvable. The problem that we're going to face here is that computational cost, yes, is going to be very low, but accuracy is going to be strongly dependent on the measurement set that we have employed within the specific environment, and also on the specific restrictions on the data set that we have employed. So therefore, if we want to apply this type of methodology, which, for example, is the one followed by methods very well known, such as Okumura-Hata, Ciabertoni, or COS231, for example, then we must compulsorily perform measurement campaigns in order to calibrate the coefficients of these methods. And this can be very costly and very time-consuming. So as a midpoint between high-grade accuracy and low-grade accuracy, but low computational cost and high computational cost, we're going to have deterministic methods which are going to be based on geometrical optics and uniform theory of diffraction. And these methods are going to make the approximation that the propagating wave front can be represented by a set of rays that are going to be following the path of the propagation vector k. And by doing this, we are going to be capable of obtaining relatively precise results whilst reducing the computational complexity. And this is interesting because this is going to allow us to analyze relatively large scenarios in a feasible way without requiring very, very large and dense high-performance computing solutions. Of course, we should take into account all of the loss mechanisms that we have within the scenario. We also have to take into account all of the electromagnetic phenomena, the material properties, diffraction from edges, diffuse scattering from rough surfaces, for example, in order to obtain realistic results. It's compulsory to note that we need to obtain this characterization because the way in which we deploy our network, this is what network topology we choose, and the way in which the environment is configured in terms of clutter and scatter elements is going to play a key role in coverage capacity estimation. So in relation with the work that I'm going to present in this presentation, we have implemented an in-house 3D ray tracing algorithm. It's actually ray launching based, so it's going to launch rays within a complete solid angle within the volume without any type of post-processing in terms of edge detection. And it's going to have tetrahedral resolution as a function of cuboid sizes. And we're going to consider all of the electromagnetic phenomena. And we're going to also take into account the dispersive material properties in terms of dispersive dielectric constant and dispersive conductivity of all of the elements inside. So even though the reduction of time is large in relation with full wave electromagnetic solutions, still, if you want to analyze indoor scenarios, for example, with a relatively large complexity or large outdoor scenarios, computational cost is still very high. So we have introduced some specific improvements in terms of reducing computational cost. One of the items that has been worked has been the introduction of neural network interpolators in order to reduce the amount of rays that have to be launched. In this way, we can effectively reduce computational time by a factor of about 80%. Another thing that we have studied is the convergence analysis of the algorithm in terms of analyzing what is the optimal ray launching resolution in terms of vertical angular separation and horizontal angular separation of rays. Also, what is the optimal amount of launched rays before extinction. This is the amount of reflections that are allowed before a ray is considered to be extincted within the simulation code, and elements such as the effective cuboid size as a function of distance. So we have done this in order to optimize the parameters and set a parameter setting that is going to give us adequate resolution whilst not increasing the overall computational cost. Moreover, we have also analyzed the impact of the application of uniform theory of diffraction, and this is interesting because in some instances, UTD can be deactivated or partially deactivated within the simulation scenarios. And this is of interest because diffraction calculation is costly, and it's going to be given as a function of the amount of susceptible edges in which diffraction can occur. that have to be taken into account within the simulator. So this has been analyzed for different type of scenario settings in order to optimize simulation code. Moreover, in order to advance in what can be the strategy to further reduce computational cost, we have also studied alternative mechanisms in order to provide hybrid simulation codes. And one of the approaches that we have studied is the computation of diffraction employing the electromagnetic diffusion equation. And in this case, what we can do is that we can apply an analytical approach based on obstacle density with an indoor environment in order to compute diffraction based on the phenomena of electromagnetic diffusion instead of full-fledged diffraction calculation. And by doing so, we can really obtain a reduction of computational cost as a function of what is the scenario size that we're going to have. Now, another alternative that we can use is going to be the use of collaborative filtering techniques, and these are basically deep learning techniques that are employed in order to try to obtain different types of patterns that we can use in order to decrease the computational cost by having patterns that can be employed for wireless channel estimation. And in this way, we construct databases of canonical scenarios, for example, specific types of room settings or hallways or pathways that can be compared with the simulation scenario under analysis. In this way, what we can do is that we can start performing calculation not by zero, but we can compare it within this framework, and therefore we can reduce computational cost by launching a few more tractable and smaller array of arrays within this scenario. And this has been analyzed for different types of configuration settings, and we have obtained the different elements in relation with the mean average error that is obtained as a function of the configuration that is employed. This is one of the latest results in relation with this application of the ray launching and collaborative filtering techniques, basically in which we have optimized what is the exact condition of the ray launching rebounds that have to be employed. And in this way, we further decrease the computational cost in order to obtain the corresponding results. Now, why is it interesting to perform this type of simulation within indoor scenarios? Here you can see an example that we computed of what is the distribution of the energy consumption for a specific type of transceiver configuration for an indoor scenario. And actually, this indoor scenario is one of our department buildings at the Public University of Navarra. And as you can see, as a function of the transceivers that we are locating within the scenario, you can see that the size of the scenario is relatively large for an indoor scenario. We're talking about approximately 1,000 square meters. And of course, all of the complexity of the scenario has been taken into account. This is all of the furniture, the walls, all of the distinctive hallways and elements such as air ducts have been taken into account. So as you can see, depending on the way in which we configure the network, the energy consumption given in the milliamps that we're going to have as a function of node location changes in a pretty, let's say, noticeable way. So it's really not trivial where we co-locate our transceivers within the scenario. So if we have the ability of obtaining the results of characterization of wireless channel behavior, we can map energy consumption behavior in the indoor scenarios. And this can be a very, very interesting result in order to fully optimize what is the consumption levels of these devices and hence the overall performance of this type of network. Moreover, here you have another example in which the simulation code has been employed in order to analyze the impact of node change location in relation to the energy consumption in terms of the milliamps consumed by the transceiver. And this has also been tested in measurement by employing magnetic current probes. And as you can see, as a function of location, there is really a relevant change in the level of consumed energy. So therefore, again, this is a very interesting tool that can be employed in order to optimize further what is going to be the network topology, because we can choose those locations that are going to be optimal in terms of not only quality of service, but also energy consumption metrics. Here you have another example in relation with coverage interference analysis, and this is the specific layout of the department building I was telling you before. And here you can see the specific 2D volumetric coverage plots that are obtained. Actually, the results are obtained in 3D, but for the sake of visibility, they're represented in 2D planes at a specific cut plane height. And here you can see that you can obtain independently the results for each one of the transmitter receiver antennas you co-locate, and therefore you can analyze the specific impact and range of each one of these antennas, and therefore analyze it in terms of not only a perceived signal level, but also potential interference that is going to be emanated from each one of these. Moreover, these can be compared with the interference background levels. Actually, on the right top-hand side, you can see measured spectrograms within this scenario. And this is interesting because it's going to help us to figure out which is the best possible channel co-location configuration of our wireless system. So, sorry. In the specific case, for example, of having an interference, we can see the case of modeling, for example, specific elements that can be interferers within the network. And here you can see one of the items that we studied, which is the interference that is generated by a microwave oven. And in this case, this was given by an issue that was seen by one of our colleagues when working with a smart cottage application in which Zigbee sensor networks are operating inside this cottage. And when the microwave oven was turned on, basically what happened was that the Zigbee network gave very bad quality levels. And we emulated what was the behavior of this microwave oven, and we can perform a hybrid simulation approach based on Huygens box, in which we can obtain the equivalent array of antenna elements that can represent the transmitting source that is given by the microwave oven. So it's like an equivalent antenna that you co-locate in the array launching simulation code. And this is what we did. Of course, full wave simulation in this case for the microwave oven was performed with the aid of CST Microwave Studio, and the current distribution was introduced in an artificially generated array that was introduced in our in-house 3D array launching algorithm. And on the bottom figure, you can see the equivalent coverage of the microwave oven. And actually, we performed measurement for quite a few meters. Actually, we measured up to 12 meters, and we could see the impact of interference capabilities was still present even after 12 meters within an indoor environment. So therefore, it's non-trivial to have our microwave oven operating in this type of scenario. Here you can see the measurement results in terms of the measured spectrum. Here you can see a specific Zigbee channel channelized in the bottom part of the spectrum. And what you can see on the right-hand side of this figure on the top is actually the time-varying spectrum of the microwave oven. So actually it's a time and frequency domain modulated source. So as a function of time, there is a frequency buildup in the spectrum. And as you can see, the components are very, very relevant. So what happens? If you don't choose adequately the channels, and actually you can see that the spectrum goes up to 2.45 gigahertz, and there's Zigbee channels actually all the way up to almost 2.48 gigahertz, what is going to happen is that your channels can get inside this region, so therefore signal to noise ratio is going to be negative, and therefore your quality of service is going to be very, very bad. If you take a look at the bottom graph, you're going to see that effectively when you choose high-level channels, they're going to be at a higher frequency. The amount of packet error rate, this is the amount of packets that are going to be erroneous, is very, very high. So therefore, it is very interesting to try to simulate and understand what is the behavior of these interference sources, which can be of any type. This is a microwave oven, but you have to consider that many, many appliances can have this capability of interference. And they can impact. And consider, of course, that we're talking about Internet of Things applications. So it's very relevant to understand what interference sources we have and model their impact in terms of wireless system operation. So let's go for some local developments, and I'm going to try to be fast here. Some of the things we've done. So, for example, one of the items is vehicular networks, and we have analyzed the impact of vehicular channel estimation. Here you can see the estimation of perceived power levels, considering the full complexity of a vehicle. And here you can see in the middle, for example, measured Doppler spectrum and the impact of varying transmitter-receiver configurations. We have also performed measurements. These are very initial measurements some years ago in order to provide vehicular ad hoc networks based on 802.11g as well as on Zigbee standard. We have also analyzed intra-vehicle connectivity in order to understand if we could use, for example, wireless body area networks for internal connectivity, not only in terms of frequency power dependent characteristics, but also in terms of power delay profiles and delay spread in order to understand the time domain characteristics. And here you can see the comparison between our relaunch encode and measurement results, and they're pretty accurate. We have also analyzed infrastructure to vehicle communications. This is a specific work that was done to analyze the viability of employing RFID connectivity in order to read up license plates that are operating within the city of Monterrey in Mexico. And of course, in order to do that, it is very important to analyze the time domain characteristics because of the inherent narrowband characteristics of RFID. So we actually performed simulation approaches in order to simulate the Doppler spectrum as a function of the deterministic channel characterization, and by employing a Monte Carlo based approach as a function of vehicle location. And here you can see some of these results. We have also characterized different types of vehicular environments. For example, this is the characterization of indoor buses, and this was in order to perform on one hand crowd sensing applications, and on the other hand in order to provide a context-aware user environment in order to be employed by our local municipality of bus services here in Pamplona. Here you can see some of these results, and again, taking into account that we are capable of analyzing energy consumption profiles, we could understand, for example, what would be the values of battery consumption inside the bus as a function of topology, and this is extremely interesting in terms of operation considerations within this type of scenario. Another example, we also proposed a single lane and crossing system, which is fully distributed among cars based on 802.11g connectivity and Zigbee connectivity, which we call test to cross. And the idea is to support vehicle riders, the conductors of the vehicles, in the case that they are transiting through non-signalized intersections, which are pretty abundant. And it is a very well-known fact that the most of the accidents with pedestrians occur in this type of intersections. So it seems of interest to try to provide a distributed system in which vehicles can exchange information in order to warn among themselves if there's going to be a situation in which, for example, a pedestrian is going to be crossing, in order to take the adequate measures and try to avoid any type of accident. So here we combine precise radio channeling approach, or radio channel analysis approach, with a specific semantic ontology in order to consider all of the specific type of events that can occur, and propose a distributed mechanism which is going to be controlled specifically by the devices that are embedded within the cars in order to adequately exchange the information within the time requirements. Another example, in this case, more centered on vulnerable road user, which are basically pedestrians, cyclists, and such, based on communication from traffic lights. And in this case, we analyzed the behavior of these systems within an urban area of Pamplona. And again, we focus strongly on radio propagation characteristics to try to understand what is the best possible location of these devices, ranges, densities, etc. Another example, again, within vehicular environments, is in relation with the introduction of wireless sensor networks inside trains. And this is given by the fact that some specific vendors of this type of trains have the requirement of providing added value services based on context-aware environments inside these train wagons. So basically, we studied the introduction of embedded WLAN and mainly W-band systems inside these trains. So we performed a full volumetric analysis of the radio behavior inside in order to consider the impact of all of the materials as well as user presence, and to see the dynamics of, for example, PICO-net formation and the way that these systems would behave in relation with Bluetooth usage. Another example is for metro lines. This specific test was performed in Bilbao in Spain, and it was basically in order to provide context-aware metro services, mainly aimed in the metro train stations and in the context of the indoor-outdoor transitions of the station as well as of the different trains. So the specific thing to consider here is the fact that multiple wireless systems have been considered WLAN transport as well as Zigbee and Bluetooth communication. Not only that, user density has also been considered in terms of deterministic user density simulation and the impact in terms of radio channel and interference analysis in order to provide, let's say, subscriber-based services that we tested in mock-up designs. One of the most recent works, which is currently in early access, has been a spatial analysis of vehicular to anything communication. And this is interesting in terms of potential services that can be provided to drivers as well as to pedestrian users within large dense urban areas. And it's very important to note what is the configuration that must be employed in terms of the transceiver location as well as the subsequent antenna sets that have to be placed and the impact that the urban buildup has within this type of environment. Here you can see some of the images in relation with the measurement setup and the analysis that has been performed by combining deterministic volumetric 3D ray launching with full-fledged statistical analysis in order to combine the results not only of wireless channel behavior, but also simulations of vehicular traffic within SUMO simulation. Another one of the items that we have worked is within the context of smart health. This is basically implementing health solutions of mobility within the framework of a smart city. And in order to do that, it is compulsory to introduce wireless communication systems to provide context awareness data related with different aspects in the treatment and the resource reservation within the medical system. So some of the examples that we have employed, this is one very initial example in which an automated electrocardiograph system was implemented in our university, and we analyzed the behavior that was expected in terms of radio channel connectivity of this device, which is an embedded electrode that is going to be communicating with a tethered Bluetooth device that will be connected via a mobile communication system. And it's relevant to understand that these systems have to provide full-fledged connectivity. And in order to do so, we must guarantee that independently of where this phone is located, because the user might have no idea on how wireless channel impact is going to impact the full system, is going to behave. So we perform the full volumetric analysis in order to guarantee perceived power levels in any type of condition in relation with mobile location and electrode location. Another one of the results that we obtained was the analysis of context-aware intensive care units, and this is a very interesting problem. Intensive care units are very complex areas that have a very strong level of instrumentation and have very stringent requirements in terms of electromagnetic emission and compatibility. But as well, they have the need of providing more flexible operations for the management of all of the pharmacology that is employed, of all of the instruments and alarms, of the access of people to this type of units. So wireless systems are seen to be very useful in this type of environment. However, the initial step here is to analyze coexistence of systems. So this was the initial result, to perform coverage capacity analysis within a real intensive care unit within our hospital complex in Pamplona, and also to analyze the interference environment. And this is very useful in order to implement future services within this ICU, which are currently underway. Another recent result is based on hospital monitoring, and this has been done in the same hospital complex, but in this case, more based on utilities. Here we have integrated LoRa networks inside of this very big hospital complex, and we analyze the capability of employing a relatively small LoRa configuration to try to connect in terms of monitoring of the supplies and of the patient movement inside of this environment in indoor as well as in outdoor configuration. Here you can see some of the results in terms of this complex wireless channel analysis and the setup that we employed with the different LoRa gateways, basically 2 LoRa gateways for this full hospital complex. Another one of the most recent results is based on the implementation of a context-aware smart campus garden in our university. And again, in this case, what we wanted to provide is the mechanisms for providing full-fledged connectivity. This means that we wanted to embed sensors basically anywhere. This included underground sensors for specific monitoring of specific soil parameters. And therefore, we performed an exhaustive analysis in terms of underground, near to ground, and over the ground communication connectivity in a volumetric scale. And here you can see again some of the details of the employed mechanisms and the full size of the scenario, which was fully generated in our 3D simulation tool. Here you can see some of the results as well as some of the pictures of the setup that was employed, which is a relatively large setup, and also the implemented framework in terms of providing the context awareness, which was based in an Arduino implemented application running within our cloud-based infrastructure at our university. Finally, one of the last results obtained is related with vehicle-to-grid communications, and this is in order to enable more optimized process of battery status monitoring in electric vehicles. And in this case, what we wanted to test is the fact of using conventional low-cost networks, basically LoRa and Zigbee networks, in order to provide this connectivity instead of using only conventional wired connectivity. So we performed an in-depth analysis, volumetric analysis of the impact in an urban area of our city of Pamplona, and we performed real measurement tests within a CAN bus mock-up in order to see if we were capable of obtaining data exchange from the vehicle to the potential data server, and this was successful. So, well, now it's work underway in order to try to continue this. So, bottom line, basically, if we want to implement context-aware environments, we really are going to work with a large set of multiple IoT deployments. And we have to work with them and we have to comply with their node capacity mobility constraints. There's a lot of challenges here. We need to comply with coverage capacity requirements. We're going to have inherent device constraints in terms of size, energy consumption, and we're going to have a limitation in the network deployment strategy. Of course, we're going to have solutions based on flexible head net configurations. We can use multiple different systems that can collaborate among them. And in order to do this, precise wireless channel is going to be very interesting in order to mitigate mainly interference issues and hence to provide the best possible coverage capacity options. Basically, we have a very interesting and exciting journey that opens ahead, which I'm sure that we are going to enjoy as a challenge. Thank you very much for your time. I hope that the talk was interesting to you. I'll be very glad to answer any question. Here's my email. Once again, thank you very much to the organization of ICMCS for the opportunity to give this talk. And I wish you all a very, very nice conference. Thank you very much and take care.